Welcome back to this lecture on recursive algorithms. In this segment, we will study our second example, namely the merge-sort algorithm, which is a very famous sorting algorithm. First, let's remember the definition of the sorting problem. The input is a finite sequence of integers, and the output is a sequence that is sorted in ascending order. Let's just assume that the sequence is not empty, since in that case the problem is trivial. So let's write down the description of the merge-sort algorithm in pseudocode. The algorithm is a function since it returns a value, namely a sequence. Let's call it merge-sort, and it takes a single argument, which is a sequence of n integers, a sub 0 to a sub n minus 1. The return type is an integer sequence, and remember they must be in ascending order. So we're going to describe this recursive algorithm. Let's start with the base case, which is when the sequence only contains one element. So if n is equal to 1, then the sequence is already sorted. You can just return the sequence as is, that is, just the element a sub 0. Now what happens when the sequence is longer than one term? Well, we have to go to the recursive case. So let's describe the behavior of this algorithm, at least at the high level, using this concrete 10 integer sequence. Well, the first step of this algorithm is to split this sequence into two sequences of approximately the same length. In other words, we're going to cut this sequence in half. So the first step in the algorithm is to compute the index of this last element in the first subsequence. Let's call this index m for middle. Well, the formula is pretty simple. We're going to take the index of the last element, which is n minus 1. We're going to divide it by 2, and then we're going to round it down to an integer using the floor function. Now, let's assume for a second that the first subsequence was already sorted in ascending order, like this. And let's further assume that the second subsequence was also sorted in ascending order, like this. Well, then the answer to the sorting problem would be pretty simple. We could obtain it by using these two subsequences as arguments to the merge algorithm that we described in the previous segment. Remember, the merge algorithm takes two sorted sequences and returns a combined sorted sequence, which is the answer to the sorting problem we're interested in. So to make this idea work, of course, we need to find a way to first sort the subsequences before we pass them in to merge. But wait a second. We have a sorting algorithm that's called merge sort. We're in the process of designing it. So what prevents us from doing a recursive call to the merge sort algorithm on the first subsequence, and then another recursive call on the second subsequence, followed by a call to the merge algorithm? Well, of course, nothing prevents us from doing that, so let's do it. So after we compute the value of the middle element index, let's do a first recursive call to merge sort with the first subsequence as an argument. Let's call the resulting sorted subsequence L for the left part of the original sequence. Then let's do a second recursive call to merge sort with the second subsequence, the one started at index n plus 1, and that goes all the way to the end of the sequence. Let's call the resulting sorted subsequence R, which is the right half of the original sequence. So now we have two sorted sequences L and R, which we can just pass in to the merge algorithm, which will return a global sorted sequence that will be the return value for the original call to merge sort. And that is the complete description in pseudocode of the merge sort algorithm. So observe that this recursive algorithm is doubly recursive since it contains two recursive calls to itself. But it works just fine because every time you call merge sort recursively, you reduce the size of the input sequence by about half. So the sequence gets smaller and smaller every time until you get to the base case with only one element in the sequence. So let's trace the execution of this algorithm on this example here. In my trace, a black box is going to represent a single call to the merge sort algorithm. So this box corresponds to the original call to the merge sort algorithm with the input sequence of size 10. So n is equal to 10 in this example. And in particular, this is the element at index n-1 or 9. So n is greater than 1. We're going to compute m, which is this element here whose index is 4. So now we're going to do a recursive call to merge sort on the first subsequence. So I'm going to draw this like this. Again, every black box represents a single call to merge sort. So what happens in this call? Well, we're back to the top of merge sort. And in this case is equal to 5. So we skip the base case and we compute m. M is equal to 2. So we split the sequence as shown here. And now we do yet another recursive call to merge sort on this first subsequence. We're back to the top of merge sort. N is equal to 3. We get down here. M gets equal to 1. And we do another recursive call to merge sort on the first subsequence. Start merge sort again with n equals 2. We jump here. M is now equal to 0. We split the sequence into two subsequences and we do yet another recursive call to merge sort. Now in this recursive call, n is equal to 1. Therefore, we're going to hit the base case and this recursive call is going to return the only element in the sequence, that is 9. And I'm going to indicate the return value of the merge sort algorithm on the second line here in the box. So this recursive call returns 9. So we just did a sequence of 1, 2, 3, 4 recursive calls, but now we're at the bottom of the recursion, and this last recursive call just returned. So we're back in this execution of the merge sort algorithm right after the first recursive call terminated. So we are right here. So what we need to do now is to do yet another recursive call on the second subsequence, namely this one. Now we're starting a new execution of merge sort, but n is equal to 1 in this case, so we just return the first element, which is 4. So now we are back to this execution of merge sort, and now we are at this point. So we're ready to do a merge of the two subsequences L and R, which are this 9 and this 4. So when merge returns, it returns the sequence 4, 9. And notice I'm going to write down the result of the merge algorithm in red on the second line of the black boxes. So then this recursive call returns the sequence 4, 9. So now this sequence is the L sequence in this recursive call. So we're at this point in this algorithm here, and now we're ready to call merge sort again on the second subsequence, which is the 8. While this recursive call terminates right away, the return value, of course, when n is equal to 1, is the first element, namely 8. So now this recursive call returns the sequence 8, which is the R subsequence, And so now we're able to call the merge function with this 4,9 subsequence as the first argument and the 8 subsequence as the second argument, and merge returns the sequence 489. And that is the return value for this recursive call, which gets assigned to L in this call. And now we're ready to do the second call to merge sort with the second subsequence, namely 1, 3. Again, we're going to start this execution of merge sort at the top. Since n is equal to 2, we skip the base case. We get here m is going to be equal to 0. And now we do our first recursive call on this sequence, whose return value, of course, is 1. Then we're back in this call. We need to do a second recursive call to merge sort on this sequence here. This one also returns immediately with a sequence 3. So when we're back in this call, we just have to do a merge of the 1 and the 3, which of course is the sequence 1, 3. Now, we just completed this recursive call, which returns the sequence R up here. So now we are able to merge the L, which is this sequence, to the R, which is that sequence, to get the sequence 1, 3, 4, 8, and 9. And that sequence is read, is returned right away at this level as the L sequence. So now we are back in the original call to merge sort at this point. So what I want you to do now is to pause the video and take a piece of paper and a pencil and write down the chain of recursive calls for the second subsequence here on the right. Now let's compare your trace with mine. I'm going to go quickly on the second half. So we're going to do a recursive call on this subsequence. We're going to split it into 2 subsequences like this. We're going to make another recursive call on the first subsequence, which we're going to split in half. We're going to make another recursive call on the first half, split that one in half, make yet another recursive call. This one will return immediately with a sequence 8. Then we're back in this call. We're going to make a second recursive call on the 6. The return value will be 6. And so the merge sequence from this one and that one is going to be 6 and 8, which is returned up to this level. And now we can do the second recursive call on the second subsequence here, which is a 7. That call returns right away with a sequence of 7, which get merged with this one, and we get 6, 7, 8. That sequence is returned as the value of L in this recursive call, which is then followed by a second recursive call on the 2, 5 sequence, which is split in half, sorted recursively, one time, second time, and then merged to get a 2, 5 sequence. And now we can merge this sequence with that one at this level to get the sequence 2, 5, 6, 7, 8. And finally, we are back at the top level with the L sequence over here, the R sequence over here. Notice that these 2 subsequences are correctly sorted. We can do a final call to merge to get the final result 1, 2, 3, 4, 5, 6, 7, 8, 8, and 9. So make sure that you are very comfortable doing this kind of trace of a recursive algorithm. Now granted, it's rather tedious to do so, but it's a good skill to practice. And even more importantly, separate from the trace, I want to make sure you're very comfortable with the way we designed this recursive algorithm, and that you feel pretty confident you would be able to design similar algorithms if you had to.